To understand the immense power of a nuclear reactor, we have to start small, incredibly small. We need to go back to the basic science you might remember from middle school, to the fundamental building block of everything in the universe, the atom. Imagine a tiny, tiny solar system. At the very center is the nucleus, which is like the sun, and orbiting this nucleus are even smaller particles called electrons, like planets. For our story, these electrons on the outside aren't the main characters. We need to zoom past them, right into that dense, crowded center, the nucleus. The nucleus is packed with two types of particles, protons and neutrons. Protons have a positive electrical charge, and they're important because the number of protons determines what element an atom is. If an atom has 1 proton, it's hydrogen. If it has 6, it's carbon. If it has 8, it's oxygen. And if it has a whopping 92 protons, it's the element at the heart of our story, uranium. Alongside those 92 protons are the neutrons. Neutrons have no charge at all. They're neutral, as their name suggests. You can think of them as the glue, or maybe the packing peanuts, that help hold the nucleus together. The protons, all being positively charged, desperately want to repel each other, to fly apart. The neutrons, along with something called the strong nuclear force, help to keep the peace and maintain stability within this crowded atomic core. Now, here's where it gets interesting. While the number of protons for an element is fixed, the number of neutrons can vary. Think of it like a bag of marbles. The number of red marbles, protons, is always 92 for uranium, but the number of blue marbles, neutrons, can change slightly. These different versions of the same element are called isotopes. The vast majority of uranium found in nature, over 99%, is an isotope called uranium-238. The 238 is just the total number of protons and neutrons added together, 92 protons plus 146 neutrons. Uranium-238 is a big, heavy, and relatively stable atom. It's not easily broken apart. It's like a well-built brick house, but mixed in with all that U-238 is its much rarer, much more important sibling, uranium-235, about 0.7% of all natural. Uranium is U-235. It has the same 92 protons, but it only has 143 neutrons. That small difference of 3 neutrons changes everything. It makes the uranium-235 nucleus fundamentally unstable. It's not a well-built brick house. It's more like a tower of blocks that's been built 1 block too high. It's wobbly. It's teetering on the edge of falling apart. And this inherent instability is the key. This special property of being easy to split apart is called being fissile. Uranium-235 is one of the very few naturally occurring materials on Earth that is fissile. It's waiting for just the right nudge to break it apart and unleash the incredible energy holding it together. But with U-235 making up less than 1% of natural uranium ore, it's too diluted to be useful for a power plant. It's like trying to start a campfire with mostly wet logs and only a few tiny dry twigs. To create a reliable, sustained fire, you need more of the good stuff. This leads to a critical process called enrichment. Enrichment is essentially a sorting process. It's a way of increasing the concentration of the wobbly U-235 atoms relative to the more stable U-238 atoms. For a typical nuclear reactor in the United States, the uranium fuel needs to be enriched from its natural state of 0.7% U-235 to a concentration of about 3 to 5%. This is done in highly sophisticated facilities using giant machines called centrifuges. Imagine a salad spinner, but one that spins at supersonic speeds. When uranium gas is pumped into these centrifuges, the slightly heavier U-238 atoms are flung more towards the outside wall, while the slightly lighter U-235 atoms tend to stay closer to the center. By carefully siphoning off the gas from the center and feeding it into the next centrifuge, and doing this thousands and thousands of times in long chains called cascades, you can gradually increase the percentage of U-235. It's crucial to understand this 3 to 5% level. This is what we call reactor-grade uranium. It has just enough of the fissile U-235 to sustain a controlled energy release, but it is physically impossible for it to create a nuclear explosion. A nuclear weapon requires enrichment to levels of 90% U-235 or more. The fuel in a power plant simply doesn't have the right physics to detonate like a bomb. It's the difference between a log in a fireplace and a stick of dynamite. Both release energy, but in fundamentally different ways. So, now we have our special fuel. We've taken raw uranium ore, we've sorted out the atoms, and we've created a fuel that is perfectly balanced, unstable enough to release energy, but not so unstable that it becomes uncontrollable. We have the wobbly tower of blocks, ready and waiting for the final piece of the puzzle, the nudge that will start it all. That nudge comes from a single lone neutron. We have enriched uranium, rich with the unstable uranium-235 atoms. Each one is a tightly coiled spring of energy. Now it's time to release it. The process that unlocks this power is called nuclear fission. Fission is just a scientific word for splitting something apart, and what happens at the atomic level is a chain of events that is both elegant and astonishingly powerful. Here's how it works. Step by step. Imagine a single, free-roaming neutron. This neutron isn't moving at blinding speeds. It's been slowed down to just the right velocity, what physicists call a thermal neutron. Think of it as a perfectly aimed bowling ball rolling gently towards a set of pins. The bowling ball, our neutron, strikes one of the wobbly U-235 nuclei. For a brief, infinitesimal moment, the neutron is absorbed by the nucleus. The U-235, with its 92 protons and 143 neutrons, momentarily becomes uranium-236. That extra neutron is the final straw. The tower of blocks, already teetering, has had one more block placed on top. The nucleus can no longer hold itself together. Instantly, it violently oscillates and splits apart. This is fission. But what does it split into? Three things emerge from this single event. First, the nucleus doesn't just crack in half, it shatters into two smaller, lighter atoms. These are called fission fragments. For example, a U-235 atom might split into a barium atom and a krypton atom. These fragments fly apart at incredible speeds, carrying a huge amount of kinetic energy, the energy of motion. Second, and this is the absolute key to everything, the split releases 2 or 3 of the neutrons that were inside the U-235 nucleus. These are the children of the first neutron, and they are born moving at extremely high speeds. Third, a tremendous burst of energy is released in the form of gamma rays, which are a high-energy form of light, like superpowered X-rays. The vast majority of the energy we get from fission comes from those fission fragments slamming into the surrounding atoms, like microscopic billiard balls. Their kinetic energy is transferred as heat. The core of a nuclear reactor isn't glowing with some magical radiation. It's simply getting incredibly, unimaginably hot because of this atomic-scale friction. But where does all this energy truly come from? This is where we see one of the most famous equations in all of science in action. Albert Einstein's E, mc2. The equation says that energy E equals mass, m, times the speed of light squared, c2. What it means, in simple terms, is that mass and energy are two sides of the same coin. You can convert one into the other. And because the speed of light, c, is such an astronomically large number, squaring it means that you can convert a tiny, tiny amount of mass into a colossal amount of energy. During fission, if you were to collect all the pieces, the two fission fragments and the new neutrons, and weigh them, you would find that their combined mass is slightly less than the mass of the original U-235 atom and the neutron that started it all. A tiny fraction of mass has vanished. It wasn't destroyed. It was converted directly into energy, according to Einstein's formula. The amount of energy released from splitting a single atom is, of course, minuscule. But there are billions upon billions of atoms in even a small piece of uranium fuel. And when you add it all up, the numbers become staggering. Consider a single uranium fuel pellet. It's about the size of the tip of your pinky finger. That one, small pellet, contains the energy equivalent of 1,780 pounds of coal, 149 gallons of oil, or 153,000 gallons of natural gas. It's an energy density that is millions of times greater than any chemical reaction, like burning fossil fuels. This is why nuclear power is so potent. But splitting one atom isn't enough to power a city. We need a way to make this happen over and over again in a self-sustaining process. This is where those 2 or 3 neutrons released during fission become the heroes of the story. This is the chain reaction. Imagine a room filled with thousands of set mousetraps, each with a ping-pong ball resting on it. If you drop one ping-pong ball into the room, it will land on a mousetrap, setting it off. That trap will fling its own ball into the air, which will then land on 1 or 2 other traps, setting them off. Each of those will fling their balls, hitting more traps, and in a fraction of a second, the entire room erupts in a cascade of snapping traps and flying balls. This is exactly what happens in a nuclear reactor, but with neutrons and uranium atoms. The one neutron that starts it all is our first ping-pong ball. It splits a U-235 atom. That split releases, let's say, 2 new neutrons. Those 2 neutrons, our new ping-pong balls, fly off, and each one strikes another U-235 atom, causing 2 more fissions. Those 2 fissions now release a total of 4 new neutrons. Those 4 neutrons cause 4 fissions, which release 8 neutrons. Then 16, then 32, 64, and so on. The number of fissions grows exponentially. This is the power of a chain reaction. But it also highlights the single most important challenge of nuclear power: control. In a nuclear bomb, this chain reaction is deliberately designed to be as fast and violent as possible. It's an uncontrolled reaction, where the number of fissions doubles uncontrollably in a millionth of a second, releasing all its energy in one catastrophic burst. In a nuclear reactor, the goal is the exact opposite. We want a controlled chain reaction. We want the reaction to be perfectly balanced, perfectly stable. We want, on average, for each fission event to lead to exactly 1 more fission event. Not 2, not 0, but 1. This state is called criticality. When the reactor is critical, it means for every one of the trillions of atoms splitting in, any given second, one of the neutrons they release will cause just 1 more atom to split in the next second. The other 1 or 2 neutrons are deliberately absorbed or allowed to escape. This creates a steady, constant rate of fission, which produces a steady, constant amount of heat. The entire design of a nuclear reactor, its every component, is engineered to achieve and maintain this perfect, delicate balance. It's about taming that mousetrap cascade, letting just enough happen to produce immense heat, while always holding the brakes to prevent it from running away. So, how is this incredible act of control accomplished? To answer that, we must leave the world of the atom and enter the world of engineering. It's time to take a tour of the machine itself. The most recognizable feature is often the giant, curved, cooling towers with plumes of clean water vapor rising into the sky. But the real heart of the plant is housed inside that other building, the one that looks like a giant concrete dome. This is the containment building, and inside it sits the reactor. There are several types of nuclear reactors around the world, but in the United States, the most common design by far is the pressurized water reactor, or PWR. Over 60% of America's reactors are this type, so we're going to focus our tour here. Let's start with the fuel itself. After the enrichment process, the uranium, now in the form of uranium dioxide powder, is pressed into small ceramic pellets. As we mentioned, each one is about the size of a gummy bear, but packs an incredible energy punch. These pellets are then stacked, one on top of the other, inside long, thin tubes made of a zirconium alloy. This metal is incredibly strong and resistant to heat and corrosion. A sealed tube full of pellets is called a fuel rod. These fuel rods are then bundled together into a square grid to form a fuel assembly. A typical fuel assembly might be about 12 feet long and contain over 200 fuel rods. Finally, hundreds of these fuel assemblies, a typical reactor core might have around 150 to 200 of them, are carefully lowered and arranged vertically inside the heart of the plant, the reactor core. This is where the chain reaction will take place. This entire core structure is housed within one of the most impressive pieces of engineering imaginable, the reactor pressure vessel. This is a massive cylindrical container made of forged steel with walls that are 8 to 10 inches thick. It's designed to withstand immense heat and pressure, and it's the first of many layers of safety we'll encounter. Okay, the fuel is in place. We're ready to start the chain reaction. But we have a problem. The neutrons that are born from fission are moving way too fast. They're called fast neutrons, and they're not very good at causing subsequent fissions in U-235. A fast neutron is likely to just bounce off a uranium nucleus without being absorbed. To sustain our controlled chain reaction, we need to slow them down. We need a moderator. Think of it this way. Imagine trying to play a game of catch with someone throwing a baseball at the speed of a bullet. It would be almost impossible to catch. But if they toss it at a normal speed, it's easy. Neutrons are the same. We need to slow them down to a catchable speed for the U-235 atoms. In a pressurized water reactor, the moderator is something very simple and familiar. Water. The entire reactor core, with all its fuel assemblies, is submerged in highly purified, demineralized water. As the fast neutrons fly out of a fission event, they collide with the hydrogen atoms in the water molecules. With each collision, they lose some energy and slow down, just like a billiard ball slowing down as it hits other balls. After just a few collisions, they are slowed down enough to be efficiently caught by the next U-235 atom, allowing the chain reaction to continue. This gives the water in the reactor two critical jobs. It acts as the moderator, enabling the chain reaction. It also acts as the coolant, carrying the intense heat away from the fuel rods. But how do we control the rate of the reaction? How do we apply the brakes? This is the job of the control rods. Control rods are made of materials that are like neutron sponges, elements like boron, silver, or cadmium, which are exceptional at absorbing neutrons without undergoing fission themselves. These rods can be inserted into the reactor core from above, sliding down into special channels within the fuel assemblies. When the control rods are fully inserted, they soak up so many neutrons that a chain reaction cannot be sustained. The reactor is shut down or subcritical. To start the reactor, the operators slowly, carefully withdraw the control rods. As the rods are pulled out, fewer neutrons are absorbed, and more are available to cause fission. The rate of fission increases. The operators pull the rods out just enough to reach that perfect state of criticality, where each fission leads to exactly one more fission. At this point, the power level is stable. If they need to generate more power, they pull the rods out a little more. If they need to reduce power, they lower them back in a bit. And in an emergency, the system is designed to instantly let go of the control rods, allowing them to slam down into the core under the force of gravity, shutting the entire reaction down in less than 2 seconds. This is called a scram. It's a fundamental fail-safe feature. So now we have a controlled chain reaction, generating a tremendous amount of heat in the reactor core. This heat is absorbed by the water surrounding the fuel rods. This brings us to the next stage, moving that energy out of the reactor. This is done via the primary loop. The water in the reactor vessel is part of a closed plumbing loop. It is pumped through the core, where it picks up heat, and then it's piped out of the reactor vessel to another major component. Now, under normal atmospheric pressure, water boils at 212 degrees Fahrenheit or 100 degrees Celsius. The water in the reactor core gets much hotter than that, around 600 degrees Fahrenheit or 315 Celsius. So why isn't it boiling into a massive steam explosion? The answer is in the name, pressurized water reactor. The entire primary loop is kept under incredibly high pressure, about 2,200 pounds per square inch, psi. That's more than 150 times normal atmospheric pressure. Under that much pressure, water simply cannot boil, even at those extreme temperatures. It remains a very, very hot liquid. It's crucial to note that this water, having been in direct contact with the reactor core, is radioactive. That's why it is contained within a robust, sealed, closed loop. It never leaves the containment building. Its only job is to be a heat taxi, to pick up the heat from the fission and carry it to the next step of the process. And that next step is where we finally start to make electricity. We've unlocked the power of the atom. We've harnessed a controlled chain reaction to generate an immense amount of heat. We've contained that heat in a loop of high-pressure radioactive water, but so far we haven't made a single watt of electricity. This is the point where a nuclear power plant stops being exotic and starts looking surprisingly similar to a conventional power plant, like one that burns coal or natural gas. Because from this point forward, the goal is simple, almost mundane: boil water. The superheated, high-pressure water from the primary loop is piped out of the reactor vessel and into a massive piece of equipment called the steam generator. A steam generator is essentially a giant heat exchanger. Inside it are thousands of U-shaped tubes. The hot radioactive water from the reactor core flows through these tubes. This entire bundle of hot tubes is submerged in a separate, independent body of water. This is the water of the secondary loop. Crucially, the water from the primary loop and the water from the secondary loop never touch. They are kept completely separate. The heat simply transfers from the hot tubes into the surrounding water. The water in this secondary loop is not under the same extreme pressure as the primary loop. So, when it comes in contact with these thousands of incredibly hot tubes, it does what you'd expect. It boils. Violently. It flashes into a massive amount of high-pressure steam, and this is the big reveal. This is the simple truth at the heart of the complex machine. A nuclear power plant is, in essence, just a very sophisticated, very powerful, and incredibly clean way to boil water. The steam produced in the steam generator is the key to making electricity, and it is completely free of any radioactivity. Its only job is to spin a turbine. This high-pressure steam is piped out of the containment building and into the turbine building. There, it is directed through nozzles onto the blades of a gigantic turbine. A power plant turbine is an amazing piece of machinery, a series of thousands of precisely shaped blades, like a massive high-tech pinwheel, all connected to a central shaft. As the steam expands and blasts against these blades, it forces the entire turbine assembly to spin at an incredible speed, typically 800 revolutions per minute. This spinning shaft of the turbine is connected directly to the final piece of the puzzle, the generator. A generator is the opposite of an electric motor. Instead of using electricity to create motion, it uses motion to create electricity. It works on a principle discovered by Michael Faraday in the 1830s called electromagnetic induction. Inside the generator are giant electromagnets spinning within massive coils of copper wire. As the magnetic fields sweep through the wire, they excite the electrons and create a powerful flow of electric current. And that's it. That is the electricity that leaves the power plant, is stepped up to high voltage at the switchyard, and travels across the country through transmission lines, eventually reaching your home. From the chaotic splitting of a U-235 atom, to the kinetic energy of fission fragments, to the heat in the primary loop water, to the steam in the secondary loop, to the spinning of the turbine and generator, we have finally converted the energy of the atom into the electricity that powers our lives. But our story isn't quite over. What happens to the steam after it has done its job and pushed its way through the turbine? It can't just be vented into the atmosphere. That would be incredibly wasteful. We need to turn it back into water so it can be pumped back to the steam generator to be boiled all over again. This is where the cooling system and those iconic cooling towers come in. The low-pressure steam leaving the turbine is piped into a device called a condenser. The condenser is another heat exchanger filled with tubes containing cool water. As the steam passes over these cool tubes, it condenses back into liquid water. This cooling water is part of a third and final loop of water. This water is typically drawn from a nearby source, like a river, lake, or the ocean. It is pumped through the condenser, where it absorbs the waste heat from the steam, and then it needs to be cooled down before it can be reused or returned to the environment. This is the job of the cooling towers. The warm water from the condenser is pumped to the top of the massive cooling tower and sprayed downwards. As it falls, a natural draft of air rises through the tower, causing a portion of the water to evaporate. Evaporation is a cooling process. It's the same reason sweating cools you down. This process cools the remaining water, which is then collected at the bottom and recirculated back to the condenser. So, that famous white cloud you see rising from a nuclear power plant's cooling towers? It's not smoke. It's not pollution. And it is absolutely not radiation. It is simply clean water vapor, steam. It's the same thing you see rising from a pot of boiling water on your stove, just on a much, much larger scale. The entire complex dance is complete. An atom splits, water boils, a turbine spins, and a light turns on. But behind this elegant process lies a deep commitment to safety, designed to handle any what-if scenario imaginable. The immense generated by a nuclear reactor demands an equally immense respect for safety. The entire philosophy of nuclear plant design in the United States is built on a principle called defense in depth. This means not just having one safety system, but multiple redundant and diverse layers of safety, so that if one system fails, another is there to back it up, and another is there to back that one up. It's a system of belts, suspenders, and a whole lot more. The safety starts with the fuel itself. The ceramic fuel pellets are specifically designed to withstand incredibly high temperatures and trap many of the radioactive fission products within their solid structure. The pellets are sealed inside the zirconium alloy fuel rods. These rods are the second barrier. The rods are contained within the massive 8-inch thick steel reactor pressure vessel. This is the third barrier, but the most visible and perhaps most important layer of safety is the one that encloses everything. The containment building. That huge dome-shaped structure is a fortress of engineering. It's typically built from a leak-proof steel liner surrounded by several feet of steel-reinforced concrete. It is designed to be the final, ultimate barrier. Its job is to contain the entire pressure, heat, and radiation of the reactor even in the most severe worst-case scenario accident imaginable. These structures are built to withstand earthquakes, floods, hurricanes, and even the direct impact of a large commercial airliner. Beyond these physical barriers are numerous active and passive safety systems. Active systems are things that require mechanical or human action, like high-pressure injection pumps that can flood the core with cooling water. But increasingly, modern reactor designs emphasize passive safety systems. These are ingenious features that rely on the laws of physics, like gravity and natural convection, to work automatically without the need for electricity or human operators. For example, some designs have massive tanks of cooling water held by valves that are powered to stay closed. If power is lost, the valves automatically open, and the water floods the core using nothing but gravity. Control rods are held up by electromagnets. If the power cuts out, the magnets release, and the rods automatically fall into the core, shutting it down. The goal is to make the reactor fail-safe. Of course, no discussion of nuclear safety is complete without addressing the accidents that are burned into the public consciousness. To understand the safety of modern American reactors, we have to honestly look at Chernobyl, 3 Mile Island, and Fukushima. The Chernobyl disaster in 1986 in the Soviet Union was a horrific event, but it's critical to understand that it happened. In a fundamentally flawed reactor design, an RBMK reactor that would never be licensed in the United States or any Western country. It was inherently unstable at low power, it used flammable graphite as a moderator, and most importantly, it had no containment building. When the reactor exploded, there was nothing to stop the radioactive materials from being spewed into the atmosphere. The accident was caused by a combination of this deeply dangerous design and a reckless, unauthorized experiment by the plant's operators. A Chernobyl-style accident is physically impossible in a U.S. pressurized water reactor. The accident at 3 Mile Island in Pennsylvania in 1979 is a very different story. It was a serious accident involving a partial meltdown of the reactor core, caused by a combination of equipment failure and operator confusion. But, and this is the crucial point, the safety systems worked. The reactor pressure vessel did not break, and the containment building did its job perfectly, containing almost all of the radioactive material. While it was a major blow to the industry and public confidence, 3 Mile Island is also, ironically, an example of the defense-in-depth philosophy succeeding under extreme stress. The most recent major accident was at Fukushima Daiichi in Japan in 2011. This was an unprecedented event. The plant was hit by a magnitude 9.0 earthquake, one of the most powerful in recorded history. The reactors performed as designed and shut down automatically, but about an hour later, the site was struck by a 45-foot tsunami that overwhelmed the plant's seawalls. The wave flooded the site and critically knocked out the emergency diesel generators needed to power the cooling pumps. Without cooling, the residual heat from the fission products caused 3 of the reactor cores to overheat and melt down. Fukushima was a stark reminder of the power of nature and exposed vulnerabilities in emergency backup power. In response, the U.S. nuclear industry and its regulators implemented a nationwide strategy called FLEX. Every U.S. plant now has an additional layer of robust, pre-staged emergency equipment, portable generators, pumps, batteries, stored in protected locations, ready to be deployed to keep the core cool no matter what happens to the plant's built-in systems. Finally, we have to talk about the elephant in the room: nuclear waste. What happens to the fuel after it's been used? After about 4 to 6 years in the reactor, a fuel assembly is no longer efficient at producing heat and is considered spent. It is highly radioactive and must be managed carefully, but it's not glowing green goo like in the cartoons. It looks exactly the same as when it went in, a solid metal assembly. This spent fuel is first moved to a spent fuel pool. This is a deep, steel-lined concrete pool filled with water. The water acts as both a coolant to remove residual heat and a highly effective shield against radiation. In fact, just a few feet of water is enough to block the radiation completely, making it safe for workers to be in the room. After several years of cooling in the pool, the fuel assemblies are moved to what is called dry cask storage. They are placed in massive sealed canisters of thick steel, which are then placed inside even more massive ventilated cylinders of concrete and steel. These casks are passively cooled by air, incredibly robust, and designed to safely store the fuel for a century or more. They are tested to withstand incredible impacts, fires, and floods. A common misconception is that the U.S. has no plan for this waste. While the long-term political debate over a central geologic repository, like the one proposed at Yucca Mountain in Nevada, continues, the current method of on-site dry cask storage has proven to be safe, secure, and robust, and it's important to put the volume of this waste in perspective. Because nuclear fuel is so incredibly energy-dense, it produces a remarkably small amount of waste. All of the spent fuel ever produced by the entire U.S. nuclear industry over the last 60 years could fit on a single football field, stacked about 20 feet high. Compare that to the billions of tons of carbon dioxide, toxic ash, and other pollutants produced by burning fossil fuels every single year. From a waste perspective, nuclear is in a league of its own. So, let's take a final step back and look at the whole incredible journey. We started with a single, unstable uranium-235 atom, a wobbly tower of protons and neutrons. We saw how a gentle nudge from a slow neutron can cause it to split in the act of fission, converting a tiny amount of its own mass into a huge burst of energy. We learned how this process is harnessed in a controlled chain reaction, creating a steady source of intense heat. We journeyed inside a pressurized water reactor, seeing how fuel rods, control rods, and ordinary water work in concert to manage this atomic fire. We followed that heat as it was transferred from the radioactive primary loop to the clean secondary loop, boiling water into high-pressure steam, and we saw how that steam, just like in any old-fashioned power plant, spins a turbine and a generator to create the electricity that flows silently and instantly into our homes. The simple truth is this: a nuclear reactor is a high-tech steam engine. It's a machine that uses the most powerful force in the universe, the force that binds atoms together, for the simple, elegant purpose of boiling water. In a world facing the immense challenge of climate change, and with an ever-growing hunger for energy, understanding this technology has never been more important. Nuclear power is the single largest source of carbon-free electricity in the United States, providing about 20% of our total power and more than half of our clean energy. Unlike solar and wind, which are essential but depend on the weather, nuclear power is a baseload energy source. It is on 24 hours a day, 7 days a week, rain or shine, providing a constant, reliable foundation for our entire electrical grid. It has one of the smallest land footprints of any energy source and an unparalleled safety record in the Western world over the last 40 years. The journey of the atom is a story of incredible ingenuity. It's about humanity reaching into the very fabric of the universe, taking a fundamental principle of physics and using it to build a better, cleaner, and more prosperous world. It's not magic, and it's not a monster to be feared. It's just physics, harnessed by brilliant engineering. And now you understand how it actually works.